Good morning. Can you hear me?
Yes, good morning, Professor.
Okay, so I want to ask you one question. Do you have the program of the course? Because in the previous years, a secretary has distributed before the program of the course. Do you have one?
Yes.
So I will probably update it a little bit, and so I will send it to you on Monday, most probably. And also next week I will give the first set of the exercises. So let us continue to discuss the theory, Fermi theory of the weak directions. I have reproduced here the Hamiltonian, which Fermi has proposed to describe beta decay. So what we have here, the Fermi coupling constant, and product two currents. Here I have written vector currents, and I put here dots, which means that actually this is not a complete story, and eventually we will see that there is also, apart from vector current, also axial vector current. There are four fields here, four fermions, which means particles with spin 1/2. When I was discussing the discovery of the particles, I have discussed really the first discovery, but then of course people have studied properties of the particles and established, for instance, that neutron and proton, they have spin 1/2, as well as we know that electron has spin 1/2, and neutrino under construction has spin 1/2. Actually, what is written here is the density of the Hamiltonian. So to say, it has meaning of energy per unit of volume. And we discussed in the end of last lecture what is dimension of GF. And we have established that dimension of GF is 1 over mass squared, or 1 over energy squared. What is the absolute value of G Fermi? And by the way, let me also comment why we are saying that once we know Hamiltonian or Lagrangian, we know everything. The point is that if you know Hamiltonian or Lagrangian, you can compute matrix elements between different transitions. And here we deal transition between initial state, which is neutron, and we are discussing beta decay. And remember, we also discussed that Fermi used the fact that nuclei are composed of protons and neutrons. And therefore, beta decay of bismuth, for instance, is the transition of one of the neutrons inside the nuclei into proton, electron, and neutrino, antineutrino. So we can write the matrix element once we know the Hamiltonian, and that will be like proton, electron, neutrino, this is final state, and Hamiltonian. So this is how we compute the matrix elements of transitions, and then knowing the matrix elements, we can compute probability, which will be proportional to moduli square of matrix element. I think you know this from quantum mechanics, or not? So do you know that when we have Hamiltonian, then using Hamiltonian, we can compute matrix elements and therefore probabilities of the processes. If not, you will learn this soon. The question is why it's Hamiltonian is so important. Hamiltonian is operator of energy, right? So that's at least part, because we have written here Hamiltonian of interaction, but of course you need to add also kinetic terms and maybe some other terms if they exist. So Hamiltonian is operator of energy, And again, according to quantum mechanics, it is operator of energy which is responsible for time evolution of the system. Okay? So we are writing a equation, or if you want, Schrödinger equation. And in Schrödinger equation, on the right-hand side, you have a Hamiltonian, right? And then you integrate this equation, and you are getting evolution of your system. So this is also generalized to the case of quantum field theory and these things. So that once we know Hamiltonian again, we can compute the amplitudes and the probabilities. In our case, we are computing decay rate because so we are dealing with this type of the process, and this type of the process is described by decay rate. Which is nothing but the probability that particle will decay in the unit of time. And according to these general rules, this gamma is proportional to a matrix element square. So it's proportional to this matrix element square. And since Hamiltonian is proportional to G Fermi, then you see from here that this gamma should be proportional to G Fermi squared, right? Because we are doing square of the matrix element. So, doing complete computations, we will have some other factors here which are known, since we know the rules. And therefore, knowing the gamma, and we are measuring decay rate, so gamma is known, measured. These other factors are also known, so once you do complete computation of your matrix element, you can find what is this G Fermi, right? So, and what has been found, that G Fermi can be represented approximately as 10 to the minus 5 over the mass of the proton. So it's easy to remember this. So numerical value of this G Fermi constant is 10 to the minus 5 over mass of the proton squared. And so we have this correct dimension. So this is proton mass. We can write this G Fermi as approximately 1 over a lambda square weak, including 10 to the minus 5, and therefore this lambda should be approximately 300 GeVs. So G Fermi is inverse of 300 GeV squared. And this is very important quantity, which we will discuss later. Now, what are other properties of the Hamiltonian? The Hamiltonian is local, in a sense that all the fields, all the components are taken in the same space-time form. So it's kind of point-like interaction, right? It's point-like interaction. All four fields are interacting in the same point. So N, proton, electron, neutrino. So they are interacting in the same point. So what are other possibilities? That's what actually Fermi proposed in the first place. We have here two currents. Alternative to this would be if we take these two currents into different space-time points. And here we can again look at the same analogy with quantum electrodynamics. In quantum electrodynamics, we have the processes of scattering, for instance, electron on proton. So again, we have currents, but they are taken in different space-time points, x and y. But to have interaction, we need to have some mediator. And this mediator in the case of quantum electrodynamics is photon, gamma. So that's mediator of interaction. This is also one of the simplest Feynman diagrams if you want. But physical meaning is the following. Electron approaching proton emits gamma and change momentum. This gamma is absorbed by proton, which also changes momentum. So you can treat this picture in this way. So what is important here, that this interaction of electron with gamma, and this is part of electrodynamics, this is fundamental interaction in QED, and this is also fundamental interaction. But what is important that you need to have some mediator which transfer interaction from the point, transfer momenta and energy from one point to another one. So this also looks like what we have in the beta decay. So we have electron, electron, and here have proton and proton. And in fact, Fermi himself already saw that maybe there is even deeper analogy with quantum electrodynamics, and maybe this process is not point-like, but also like in quantum electrodynamics, there is some mediator between two currents. So, in this way, one can think that neutrino and electron current, neutrino-electron, taken at point x, interacts with current of neutron and proton in another point y, and there is some mediator which connects point x and point y, and these mediators are, we kind of denote this as W bosons. So I have written this kind of diagram for scattering of neutrinos on neutrons, but just from algebra of the process, that corresponds also to neutron decay. So what happens is that neutron transforms to proton, and then there is a W boson, and W boson, here it will be W minus, it is transferred into electron and Einstein neutrino. So this is beta decay. This is beta decay. Here is actually the same process, the same vertices, the same interactions, but just algebra of reactions here is neutrino in the initial state, and this type of the diagram describes scattering of neutrinos on neutrons. Questions? So everything is clear. Now, so the point is that instead of these point-like interactions, we can consider interaction of N, P. I just inverted this diagram. W, and here we have electron, and here we have neutrino. And neutrino can be in the final state. Now the question is, what is difference between diagrams when we have point-like interaction and exchange? So everything depends on the mass of the mediator. So what is the mass of the mediator? If we have some mediator of a given mass m, then it can propagate distances, virtual particle, I will explain this, as 1 over the mass of the W boson. So, of course, what happens here, if you have, for instance, neutron, which is transformed to proton, and we have emission of W boson, and the masses of these two guys are nearly the same, the particle, which is emitted from this vertex, is virtual. Who knows what is virtual particle? It's not on the mass shell. In contrast of particles on mass shell, when you have the relation that energy equals p squared plus mass squared, you may have virtual particles which actually do not satisfy this dispersion relation. And so these particles may exist only finite period of time and distance. And this W boson, if it is massive, that can propagate distances at most incomparable with 1 over the mass. Question? So you can take this for time being as kind of empirical rule, but you will certainly learn this in great details in the quantum field theory course. So that, I'm discussing this to make the following point. So if mass of the W boson is very big, then this W boson cannot propagate long time. So essentially, you have something like this, W boson, and these are final particles. So that distance is 1 over the mass of the W boson. Now, if you have low energies, and in the beta decay we deal with energies in MeV scale, and we will see later that mass of the W boson is in GeV scales, in many orders of magnitude bigger, then this interaction looks like point-like. So with these external particles, energies of external particles, de Broglie waves are quite big. And what you have is the following. You have big de Broglie wave of this size, and a very small region of interaction. And therefore, with this big de Broglie wave, you do not feel that these are two different points. It will look like a single point. This is like if you have microscope with bad resolution. If you have microscope with bad resolution, which has the wave which is bigger than the size of the structure you are considering, then it will look like a point-like. So, which means that although at lower energies the interaction looks like a point-like, in fact, what is behind this point is this exchange of W boson. The Fermi already kind of understood this, and what he was saying is that, okay, so we are in a regime where the radius of weak interactions is much smaller than the lambda de Broglie wave of particles involved, proton or electron. So in this range, the interactions become like point-like. Looks like a point-like. there is another interesting and important consequence of this picture. And the consequence is that according to, let me write this again diagram, sorry. So again, and P, and here we have nu and electron. Now instead of 4 fermion interaction, we have interaction which is similar to what we have in electrodynamics. So it's 2 fermions, and actually W boson has a spin 1, so that's how it was introduced, and therefore it's very similar. The only difference is that photon is massless and has 0 electric charge, while W boson is charged because, you know, in this vertex there is a change of the charge, and therefore this guy should be also charged. So this has 0 charge, this is plus, and if this is emitted and propagated in this way, the charge is minus. Now we have 2 vertices similar to what we have in electromagnetic interactions. And then coupling constants are dimensionless, as in the case of electrodynamics, G and G here. But we have propagation of a particle between these 2 vertices. And what corresponds to this propagation, at least at low energies, is mass of the MW boson squared. This comes from the propagator, that's approximately. Again, you will learn this soon. So which means that instead of G Fermi, in the case of 4 fermion interactions, you have G squared, because you have 2 interaction points, over mass of the W boson. So this, how Fermi coupling constant is interpreted in the picture when you have the diagram with exchange of W boson. So now we understand where dimension of GF comes from. So it comes from this propagator, or from mediator of interactions. Questions? So it looks like, again, it's quite, so let me see. Should be another speaker. Yeah, tell me. Exactly, it's like electric charge for these interactions, because the structure is the same, you see. So this interaction is the same, similar to what we have in electrodynamics, when we have charge fermions, for instance, electron, and emission of gamma. Here, we have this N go to P, or neutrino go to electron, and then we have, again, vector particle. Again, you see this very, very similar to what we have in electrodynamics. I told you that this theory was, to a large extent, introduced in analogy with electromagnetic interactions. So actually, Fermi even made estimation of what should be the mass of the W boson, because you know what is G Fermi. You measured this, say, from rate of the decays. If G is of the order 1, then the mass of the W should be around 300 or 30 GeVs, 30 times heavier than the proton. So now we know that G is not 1, so this is for G equals 1. it's smaller, and therefore mass of the W boson is bigger. No, sorry. So what? Let me repeat. So again, Fermi made this estimation assuming that G is of the order of electromagnetic coupling constant. He really wanted to go till a beaten end with analogy. So if G is electromagnetic charge, then the mass of the W boson should be around 30 GeVs. And we know now that G is bigger than E, and therefore mass of the W boson is bigger than this 30 GeVs. We will discuss this later. So that's kind of was deviation from the mainstream of lecture. I just gave in advance announcement what could be behind this Hamiltonian, but let's come back to this Hamiltonian, which is just point-like. And let me summarize. So what are kind of principles of construction of this Hamiltonian? Let me just remind you. This is analogy. With electromagnetic interactions. It is constructed to satisfy Lorentz invariance. Right, so we have these connections of mu. So it's constructed in such a way that it conserves the charge electric charge. Another one is simplicity. So this is the minimal what you can imagine, because you have 4 fields or 4 particles involved in beta decay. This is the Hamiltonian density, which means the energy density of the interactions. And of course, if one of these fields is absent, then there is no such an interaction, there is no interaction, and therefore Hamiltonian should vanish. So it's just minimal product of 4 fields. Now, he has written this Hamiltonian to describe beta decay, but it gives also some predictions. So this is very important. It's not only that you reproduce results which you started with, but it also has some important consequences. By the way, first of all, knowing this Hamiltonian and performing computations, you can compute energy spectrum. Energy spectrum of electrons in beta decay. And computations were in very good agreement with observations. Remember, we started with these paradoxes, and one of the paradoxes was continuous spectrum of electrons, which has such a shape with some endpoint. And computations with this Hamiltonian reproduced such a dependence very well. Although Fermi used just gamma without this parity violating terms. So in a sense, he used a bit wrong Hamiltonian, but nevertheless got a very good description. And this happens because he made the computations for unpolarized particles. And these additional terms, and we will learn this later, they show up in the case when you fix some or make polarization of particles. Then these terms become important. When you do not make polarization and just sum up or average over possible polarization of particles, then these additional contributions disappear. And you get a correct spectrum even with just a gamma mu here. As I started to say that this Hamiltonian actually not only describes beta decay, but it also tells us that some other processes exist. In particular, electron antineutrino can interact with proton, produce positron and neutron. This is algebra of reactions. So we have these fields, and the same Hamiltonian actually describes some other processes. You just put fields in the initial or final state, changing this arrangement. Actually, this process comes from Hermitian conjugate, because here proton is absorbed, and here is proton is emitted. So this process is called inverse beta decay. Very important process, and even now we are studying in details and using this in many cases. So this is inverse beta decay. Yet another prediction is E-capture, the process when you have electron interacting with proton, and you have final state with neutron and neutrino. Again, this is algebra of reaction. So, for instance, in comparison with this process, you put a positron in the initial state and then change positron onto electron, and neutrino put in the final state. I put here E. This is correct identification for this process. Although in the time of Fermi, it was not known that neutrinos are in different types, but I'm writing what we have now already understood. And of course here I should write also electron neutrino. So this is called electron capture. Also an important process. So it also exists, for instance, in atoms. You have atom, and one of the electrons from atomic levels can be captured by nuclei, and then nuclei, of course, changes because one of the protons become neutron, and neutrino is emitted. Okay? And eventually all these processes have been found, and that is really confirmation of Fermi theory. Questions? Interestingly enough, that in spite of success of Fermi theory in this description of beta decay, still people were in doubt that neutrino really exists as true particle. So some people saw that, well, neutrino is some kind of effective phenomena, some kind of reflects some non-trivial dynamics of interaction, but not really true particle. So that was one of the objections. It was also motivated by the fact that although neutrino is neutral particle, it still may have magnetic moment. And therefore, it still may have electromagnetic interactions due to the existence of non-zero magnetic moment. But it was also observed that there is no such a type of the interactions. That was actually one of the motivations for Majorana when he introduced this Majorana particle, Majorana neutrinos, because in the case of Majorana neutrino and antineutrino coincide, and in this situation, magnetic moment is exactly zero. So you see, it was a long period of accepting this idea of neutrino. So what is really true or final proof of existence of neutrino as a particle? There were some criteria which actually should be satisfied to prove that neutrino is really a particle and not some kind of phantom phenomenon. So to show that neutrino is true particle, one needs really to prove that this particle is propagating, right? So it is produced in some point x, propagate, and interacts with another point y. Because in the beta decay, we saw that something is emitted, or neutrino is emitted, but it was not clear if something which is emitted really propagates and interacts. So that was an objection. So probably we need to change the theory in such a way that a neutrino is just something phantom object, just to to have correct features of beta decay. So you need to show that neutrino propagates. You need to show that it interacts in point y, so this is production point, and this is detection point. So it should interact in a point y, and it should transfer energy, momenta, and quantum numbers from point x to point y. Then everybody is convinced and agreed that we are convinced that this is really true particle. So it propagates from production point to detection point. You need to observe that here, in interaction, neutrino delivers some energy and change quantum number. So neutrino, we will discuss later, has lepton number. And therefore, it should affect lepton number in final state. What was suggested is the following to realize this type of setup. It was suggested to use beta decays as the source of neutrinos. So here in the source, you have beta decay, or decay of nuclei, and decay of neutrons inside the nuclei. Then put the detector at some distance, say a few meters for instance, and use inverse beta decay to detect neutrinos. So this is detector. And what we have here, try to find the interactions of these antineutrinos produced in the beta decay with protons, with emission of positron and neutron. So to use inverse beta decay to detect neutrinos. Actually, in these days, this is one of the main reactions for detection of neutrinos. And new experiments will come soon, and a number of experiments are running now which use precisely this setup. For instance, people are studying neutrinos from atomic reactors. We will discuss this probably next lecture. And precisely this type of setup is realized. So there are nuclear reactor in which you have beta decays, which produce this anti-neutrino flux, and then at some distance, inverse beta decay, or some kind of this type of scattering of anti-neutrinos on protons, is used to see interactions. Actually, these two products are very nice because it's easy to detect positrons and neutrons. In 30s, when people already discussed this, it was realized immediately that the probability of interaction, so people did computations, of course, of the probabilities of this process, was extremely small. So one of the first computations was by Hans Bethe and Piles. And then computed cross-section of this process of scattering of antineutrinos on protons. And they have found that the probability is so small that you need to kind of astronomical layer of water to have interaction of the order 1. So the probability of interaction of the order 1 for neutrinos of these energies is of the order of 1 if you have a layer of the say water of the size of 1 astronomical unit. And by that time it was kind of conclusion that probably neutrinos will never be discovered. So keep this in mind, this lesson. So of course neutrinos were discovered, and now we have millions of events with neutrinos. It's kind of routine detection. We have detailed study of neutrino interactions with huge number of events, and you will see the progress done to achieve this goal. So let me compute cross-section for you of this inverse beta decay. And so we will have now kind of technical considerations before we will come to detection of neutrinos. So let me discuss cross-section. Actually, this consideration is general. It's not only for neutrinos. You can use the same for other interactions. So cross-section. Suppose you have amount of matter, so it's your detector, of the length L, so this is the length, and density n, so this is density of particles here on which, say, our neutrino interacts. And neutrino is coming, so this is setup, general setup. There are particles, protons actually, for our reactor, for our process, reaction, and neutrino interact with particles inside this volume. So what is the probability of interaction of a given neutrino? So we are considering now a single neutrino and see what is the probability that it will interact in this volume. The probability will be proportional to distance, to size of this detector. It's clear, right? That the bigger the size, the more probable it will interact. It is proportional to density. Of course, the bigger the density, the more you have scatterers, and therefore the bigger the probability of interaction. And let me introduce some other factor, sigma, This is what we call cross-section. And cross-section characterizes interaction with individual scattering. So, sigma characterizes interaction with individual scattering. So we introduce cross-section in this way. So once you know cross-section, then you multiply this by density of scatters and the length, and then you get the probability. Now, according to this formula, cross-section has the following dimension. Probability has dimension, is dimensionless. Now, this has dimension centimeters. This is 1 over centimeters cubed, and therefore sigma should have dimension of centimeters squared, or inverse of mass. This formula is valid when the probability of interaction is much smaller than 1. The resulting probability is much smaller than 1. Because, so we are counting in this way all the scatterers in our volume along L. Of course, if the interaction is very strong, you will have already significant absorption of your neutrinos in the first layer already, somewhere in the beginning, and therefore, instead of this formula, you need to use integral. So, qualitatively is the same. For neutrinos, it's certainly valid because the probability of interaction of neutrino, even is kind of huge volumes of lengths of the matter, is very small. But in general, you need then to use small layer, introduce this for small layer, and here, instead of writing L, you need to put dx and then make integration over dx. Okay? But for us, it's enough to use this formula once we are discussing neutrinos. So this formula has also very simple classical analysis, or classical interpretation. Sigma can be considered as the product of area occupied by scatter so to say, each of the scatterers we can consider as some area, and neutrino is say moving and the particle is moving, and if it hits this area, then it interacts. Multiplied by opacity. So, even if your particle hits the area of scatter, it may still pass through if it is not completely transparent. So if it is still partially transparent, then it can pass through. If it is really completely opaque, then this opacity is just 1, right? However, it may happen that the interaction is weak, and therefore, although you hit this area, particles still can come through, and then you need to introduce this opacity. Then the probability, now I'm coming to interpretation of this formula, can be written as total area occupied by scatterers over the total area. So here you need to sum up all the scatterers. So let's come and to see our detector. And so neutrino is coming in this way, and what it sees these areas with scatterers. And then the probability will be given by total area of these scatterers, so you need to use each of these scatterers, sum over all these scatters, and divide over total area. So then you will have a probability. Essentially, this is what is written in this formula, because L times N is nothing but precisely number of scatters. This is number of scatters if you take this to be a unit of area. So 1 centimeter. And then you multiply this by sigma, which is the area of each of the scatters. And then what you get this probability. So this formula has very simple classical analogy, classical interpretation, as the sum of areas occupied by scatterers over the total area. Okay? Now let me compute cross-section for the process of inverse beta decay. And I will compute this cross-section for neutrinos with energies in the range of few MeVs. This is precisely typical energy of neutrinos emitted in beta decay of nuclei, and that's what is used actually in many experiments. So, cross-section for MeV scale of neutrinos. So the process is that we have neutrino, which scatters, produces positron, and then transform proton into neutron. So this is the process which we are considering. Cross-section is proportional to the amplitude of the process squared, which is, in our case, final state is A plus and neutron, then Hamiltonian of interaction, and initial state is antineutrino and proton. So we need to compute this matrix element, so square, and then also we need to take into account what is called phase volume. So we need also to integrate our possible momenta and energies of particles in final state. This is why I have written here this proportionality sign. So what we can say immediately, then sigma, and I already mentioned this, is also proportional to G Fermi squared. Since the Hamiltonian is proportional to G Fermi, then cross-section should be proportional to G Fermi squared. Now let me explain logic. Actually, I will use this many times, and I want you to appreciate this well. What I will use, to some extent, first, dimensional arguments. Because, so you are not at the level to make derivation to compute these matrix elements, for time being at least. Nevertheless, we will get results which are very close to really exact results. So I will use some physical arguments. If you want, I will introduce for you physical derivation of cross-section. So let me first do this, and then I will explain a little bit more about these things. So we have this proportionality. Now, exact expression for sigma should be G Fermi squared times x. Some quantity x. Clearly, this quantity x should have dimension. What should be the dimension of x? We know that sigma has dimension centimeters squared, right? Let me write here so that I'm using dimensional arguments. Well, this is very important trick again. So you can derive many things or check many things using dimensional arguments. So sigma has dimension centimeters squared or 1 over the mass squared. G Fermi has dimension 1 over the mass squared. We have here squared, then this is m to the 4th power, which means immediately that dimension of x should be mass squared or energy squared. Okay? Now, which energy should we use here? So it should be some energy squared. So what are parameters in our problem of dimension of energy? So we have mass of the electron, right, in our problem. We have energy of neutrino. And we have mass of the proton. So these are the only available quantities of the dimension energy. And therefore, x should be somehow composed out of these values, quantities. Agree? Well, stop me if you need to have some explanation. So the logic is the following. First, I have obtained that the dimension of x should be mass squared or energy squared. Then I'm seeing what are the energy of quantities of the dimension of energy in this problem. And the scattering, and this is energy of neutrino, mass of the proton, so proton is at rest, roughly speaking, and mass of the electron, which appears here. Of course, you can say that also mass of neutron is important. Okay, we can do this also. Now physical arguments. Now we need to select, so which kind of combination of this energy parameter should be written instead of x. So first observation is that the energy of neutrino is much smaller than the mass of the proton. Right? So energy of neutrino is MeV, while the mass of the proton is 1,000 MeVs. Right? At least 2 orders of magnitude. This means that I can neglect all kind of recoils of proton, and consider essentially that the mass of the proton is infinite. It doesn't take any energy. And therefore, this means that x should not depend on the mass of the proton. Second argument is that the energy of neutrino is much bigger than the mass of the electron. This is not completely true, but to a large extent it's true. Imagine that you have energy of neutrino 5 MeVs, and the mass of neutrino electron is 0.5 MeVs, which means that the energy of neutrino 1 order of magnitude bigger than the mass of the electron. And therefore I can neglect mass of the electron. And therefore, the only what is left is the energy of neutrino. And so, conclusion is that up to coefficients, x is energy of neutrino squared. Do you like these arguments or not? Therefore, the cross-section is given by G Fermi up to constant square over energy of neutrinos squared. This is actually a very solid derivation. You will have some experience later, and I think you will appreciate eventually. First, it's quick, right? And it's almost exact. So what is exact formula? Exact formula is sigma equals GF square E nu square multiplied by 1 plus 3GA square over 3 pi. And what's interesting that this additional coefficient on the top of this dependence which we have derived is just 4 over 3, close to 1. So in this way we have derived expression for cross-section with accuracy of the order 1. But what is important, we obtained correct dependence of the cross-section on energy. It is the same as we have in the case of precise computations. Now, what are the factors here? Even these factors, I mean, those who have some experience in doing computations can essentially reproduce all these factors. So this one actually comes from the fact that we have not just vector current, but we have some axial vector current. So I haven't discussed this. As I told you, the correct expression is gamma 1 plus GA gamma 5 for hadronic current, for current neutron go to proton. So we essentially computed this one, but you have this additional contribution to the currents, and that gives you this GA squared in cross-section. And this one, 3, is also kind of can be understood because this part is sensitive to the spin of particles involved. And total spin is 1 here because we have particles with spin 1/2. And this essentially, this 3 reflects 3 projections. This one, this factor comes from integration of the phase space. Again, when you compute cross-sections or probabilities, eventually you need to integrate over momenta in the final state. And here we have momentum of neutron, momentum of positron, and then you have here 2 pi cube, 2 pi cube, and you have some pi here. So this is, probably you have learned these factors in relativistic quantum theory, quantum mechanics, but you will certainly learn this in QFT. So this is integration over momenta in a final state, because, you know, in final state, the energies and momenta, these particles are not fixed, right? You may have different sharing of energy of initial state between these two particles. And if you consider total cross-section, and here we are considering total cross-section, which means that we need to integrate over final variables, final energies and momenta. Of course, we can consider also differential equations and try to see what is the distribution over energies of these positrons. Then we should not do this integration. But what we did, we computed total cross-section. And therefore, we should make this integration. Of course, some pi will appear when we will integrate over angular variables here. And in the end, what we will get is 3 pi. So the person who has experience can tell you exactly what should be degree of pi here. So you see, in principle, you can get final answer almost precise without doing real computations. And actually, if you try to make computation, you will spend, say, at least 1 day with all these checks to get this result. And we are getting this in 5 minutes. You can use this trick in very different ways. For instance, to check if your computations are correct. You are doing computation, lengthy computation. You get some answer. And how to convince that you didn't do any mistake? So then you use this type of physical argument, physical derivation, to confirm that your computations are correct. Again, very important thing is that dependence of crucial parameters is known here, and you can get it correctly. It's E squared. It's important, very important observation that neutrino cross-section increase with energy, which means that although the energy interactions at very low energies are very small, with increase of energy, the cross-sections, and therefore the probability of interactions increases rather quickly. So although this increase is not forever, so it changes by actually 2 times. First it changes to linear, and then it becomes even kind of logarithmic or coming to the constant. Again, this formula is valid when the energy of neutrino is below the mass of the proton. So we have derived this. When the energy becomes comparable, energy of neutrino, with the mass of the proton, this formula should change. I think I had even some exercise to do this. Questions? Everything is clear? Maybe then I should not, because sometimes people are objecting, so look at this is hand-waving arguments, but this is not. This is what I want to convince you. So these are serious arguments, and if you do computations and getting something different which actually contradicts to your simple estimation, most probably you are wrong in your lengthy computations than in doing this type of the estimations. Well, actually, this type of methods, or even more advanced methods, has been developed recently in the approach which is called amplitudes. Again, the idea is to make computations without real computations of integrals on the basis of, again, dimensional arguments, knowing spin variables and angular momentum conservation, symmetries, because sometimes you have symmetries in your problem, and that helps a lot if you have symmetries. And the point is that using all these things, you can almost completely perform computations without doing a real, say, QFT computations of matrix elements. Let me add to this argument the following. Actually, we'll need this formula for one of the exercises. So what is complete computations in quantum field theory? You start with Lagrangian, or computations in QFT. And you want to compute observables. So eventually what we are computing, cross-sections, probabilities, things like that. This is what we are observing, some distributions, energy distribution, momenta distribution, things like that. So you do QFT computations according to well-elaborated rules. You can use Feynman diagrams. And usually this is quite lengthy. Of course, for this process, things are simple, but when you compute more complicated processes, that may take time. Eventually, you get observables. And these observables, like cross-sections, gamma decay rates, probabilities, they are functions of kinematical variables. So eventually you get these like a cross-section, and cross-section is some function of momenta of particles involved and spins of the particles involved in the process. So final answer depends on kinematical variables, not what is inside your theory, but eventually you are computing variables as functions of outer momenta and spins. Also, it should depend, of course, on coupling constants which are entering here. So you can do this pass, but you can do kind of straight pass and try to compute without this intermediate, starting from Lagrangian, and you can get a final result. Because eventually your final result should be the function of energies and momenta and spin polarization, etc. Okay? Well, actually, I will derive several such an observables during the course. Questions? So in the end of this lecture, I want to introduce some more general kinematic stuff which is useful to, important for making computations. So what I want to show you how to compute number of events produced by flux of particles. Let me remind you that what we did before, we had just a single particle which is entering our detector, and we computed what is the probability that this particle interacts. Now we have the following setup. Again, we have the detector. With the length L, number density of particle n, and the area, which is also important when you compute the number of events, of your detector n. So it's the area of this face of your detector, front area of your detector. And you have particles, or flux of the particles, which enter your detector. For instance, neutrinos. So this is what we are usually having. We just have not just single neutrino, but we have flux of neutrinos. For instance, flux of neutrinos produced an atomic reactor, which is huge flux of neutrinos which fall down onto the detector. So, and what we want to compute is the number of events in the unit of time for a given flux produced inside the detector. So we introduce F, which is density of the flux. So, and this is number of incoming particles which are crossing the unit of surface in the unit of time. So we take here unit of surface, and then F is number of particles or neutrinos which cross this unit of surface in the unit of time. So this is what we call density of the flux. And density of the flux has dimension 1 over centimeter square over second. And of course, total flux of particles entering the detector is given by density of the flux multiplied by the surface. So this is total flux. Now let us compute rate of events. That is number of events in your detector in the unit of time. That's what you are usually interested in. Rate is given by total number of events produced over the time of exposure or observation. So let me say this is rate, this is total number of events produced in your detector during all the time of observation, and T is the time of observation. Again, this analysis is valid for any process, like we compute for LHC number of events, and there's exposure time or the time of observation. It can be, say, 1 year, and then we compute first the number of events during 1 year, and we can introduce the rate, which is number of events per unit of time. Now, what is this R, rate of events? It is given by the probability of interaction of individual particle multiplied by total flux, F times S. So this gives to us number of particles, and let us consider the situation when we have a uniform flux, and which is also time independent, so it's the same. It's constant flux, uniform flux. Then F multiplied by S is total number of these particles entering your detector per unit of time. Multiplying by the probability that each of these particles interact, we will get rate, which means number of interactions of our flux inside the detector in the unit of time. So this is the probability which we have discussed before. Probability of interaction of a single particle, single neutrino, of single entering particle. And this is again the number of particles which enter per second your detector. And again, this kind of requires that the probability is smaller than 1. Otherwise, again, you need to make integration and just multiply by this factor. Now we have expression for this probability derived in the beginning. We can insert this, and this probability, as you remember, is given by cross-section, multiplied by number density, multiplied by length, and then we have factors of flux factors, F and S. So here I inserted expression for probability. This is one. This is what we have derived before. And so we have this expression for the rate. Now, you see, L multiplied by S gives the volume of the detector. That's volume of the detector. It's volume of the detector. Now, multiplying by n gives me total number of particles, scatterers in the detector. So, n times L times S is total number, let me put it here, that we produce. So, n, which is density, L, S, so this is volume. And this gives me total number of scatterers in my detector. So, which means that this derivation doesn't depend on really on configuration, unless the flux is not isotropic. And then the rate can be written as cross-section multiplied by n and multiplied by density of the flux. So this is very common formula which is used to compute the rate of events. Total number of scatterers in detector, this n, cross-section, and density of the flux. So this is the rate, and therefore the total number of events during the time of observation is given by rate multiplied by t. I think I will stop today at this, so tell me if you have questions. And this type of the formulas, you will need them to solve some problems also. But this is what we are using in particle physics, of course. Questions? To this part or to the previous parts, please tell me.
Professor, I didn't get when we had the mass of the proton close to infinity.
Yeah.
Why we didn't consider that for X? Can you explain it again?
Why we do not consider this for
X, when we had the...
What is X?
The cross-section was equal to EF squared times X.
Well, X is some kind of unknown. I'm saying that I just introduced this X temporary to denote something which should be put together with GFM. And then I'm showing that this should be the energy. Now, the point is that for low energy neutrinos, proton mass is very big, is too heavy. Exact expression for cross-section depends on this mass of the proton, and it depends in the sense that you have kind of recoil effect, which means that your neutron, more precisely, so you have a proton which then transforms to neutron. And if neutron is moving, then you need to take into account, and eventually this will enter into expression. However, so if you do these computations exactly, then you will have some additional terms which will be suppressed by energy of neutrino by the mass of the proton. So the bottom line, you have your sigma, which we computed for infinite mass, but then corrections will be something like this, energy of neutrino of the proton mass or even square of this. So the corrections will be small. Physically, this means like this. So if you neglect the neutron recoil, then what you have some particle which is staying, which is not moving, and it is staying, it's not moving, and therefore it doesn't enter dynamics of the process. Okay? And therefore, in this approximation, a result of the scattering should not depend on the mass of the particle. So when you go to infinity, then in infinity you cannot put this in your formula, right? I don't know if it's clear or not. But again, exact computations would lead to some corrections if you take mass of the proton infinity, then this term disappears. If you take finite still mass of the proton, you will get correction to your result of which are suppressed, or much small. So saying that a proton has infinite mass is equivalent of saying that we neglect this type of the corrections, which is, say, 1% or even less than 1%. But again, physical reason is that for energies of neutrinos, when you can neglect recoil, essentially the energy and momenta of proton doesn't enter dynamics of the process and scattering. To convince, again, you should write energy momentum conservation. There is nothing complicated, and to see what is the energy of a neutron which is acquired. It's very small, and you can always neglect. This cannot be done if the energy of neutrino becomes comparable with the mass of the proton. Then what is interesting, the cross-section also changes the sign. Cross-section will be different. And what you have at low energies, the cross-section is proportional to square of energy. However, at the energies of neutrinos of the order of mass of the proton, that becomes, so it first increases like this, and then it becomes linear. So dependence becomes linear, not quadratic. Here's quadratic, and then it becomes linear. Okay, more questions?
I have a question.
Mm-hmm.
In the cross-section formula, the term of the coupling constant is valid for all other production forces. I mean, there is GA square over 3 pi. This term is, how should we find these terms?
I'm not sure that I understood correctly. So we have G Fermi, which is coupling constant. It enters cross-section as G Fermi squared. And it enters in this way for all the processes which are induced by this or produced by this Hamiltonian.
Yes, but there is another additional term, 1 plus 3g
yes.
squared over 3 pi. I computed about this term.
Well, yeah, okay. So still you have G Fermi squared. So what you have is G Fermi squared, and it is staying. But on the top of this, you have here E squared. You have additional term, which is 1 plus GA squared 3, and here is 3 pi. So this is our formula. Now, this term, this additional term, you still have this G Fermi square. That's no question. This term appears when you take correct expressions for currents, because remember we had proton, gamma mu, neutron. So that was our current which we used. This is not complete expression because exact, and I have written for you exact formula. Exact current has the form P gamma mu 1 plus GA gamma 5 n. So this is what Fermi used. And this is what we used in my naive computations. But it's not whole the story, because exact current, and that was established later after Fermi produced his theory, that the current is not like this, but the current has such a form with additional term GA and gamma 5. And the origin of this GA, and I have written you exact formula when you use complete Hamiltonian, that originates from this GA times gamma 5.
Okay, is it just use it for inverse beta decay?
No, it should be for all the processes which are produced by this Hamiltonian. So GA, this term should appear everywhere. It's additional term. So to say, roughly speaking, you see, you have here a contribution from vector current, but you need to add also this. So naively you would say, okay, I have to multiply my expression by 1 plus GA squared. But this is more complicated because you have here gamma 5, and actually this is related to spin variables. And therefore you have this expression 3 times GA. And actually GA, that I have probably not written, is something like 1.2, 1.23. But it depends, this G also depends on what is the nuclei you are using. If you are using free nucleons, or say neutron, or it is nuclei. And even now it's a big deal to actually understand what is correct value of GE. So I could actually, if I would do computations, I could actually also derive for you this term. As I said, because factor of 3, of course I should have some contribution which is proportional to GA squared, but since this, with gamma 5, this term affects spin variables. So these 3 just corresponds, there are 3 projections of the spin 1. So we have particles in the initial state and a final state with a total spin 1. We have 1/2 and 1/2, which gives total spin of the state of initial and final state 1. And so it has 3 possible projections. And this is the origin of this factor of 3. So again, with experience, I can actually derive this formula without any computation, just using physical arguments. Okay? More questions? Well, as I told you, actually I sent mail to Giovanni, I haven't seen him, asking to clarify if, say, these 2 people can sit down here. But anyway, starting from the next week, I will meet each of you individually and just to discuss, and you can express your opinion also, what your recommendations, how I should, if you are satisfied or not, of how I'm displaying material and things like that. So I will on Monday give you the updated version of the course, I need to see what actually you have in your hands. And also next week I will give you the first set of the exercises to solve. Okay? Okay, so then good luck. See you on Monday.
Yeah.